Describe in brief the main components of the atomic absorption spectrophotometer. The main components of the atomic absorption spectrometers include: first, source of radiation. Source of radiation is hollow cathode lamp. It consists of a glass jacket containing cup-shaped cathode made up of the same element which is under study. A tungsten wire or plate acts as anode, which is arranged in the same glass jacket. The glass jacket is filled with the inert gas like neon or argon at a low pressure. When a potential of 500 to 1000 volt is applied between the two electrodes from the power supply, the atoms of the inert gas is ionized. The positive charge ions start moving towards cathode. These fast moving ions remove the atom from the surface of the cathode. This process is called sputtering. These metallic atoms then collide with highly energetic gas ions, and some of them get excited. These excited metal atoms emit their characteristic radiations when they return back to the original state. Second is a rotating chopper. A rotating wheel breaks the beam of light coming from the cathode lamp and produces intermittent light, that is, broken lights. Next comes burner. The flame is produced by burning the fuel with the oxidizer, and the sample is burnt. Burners used are of two types. One is total consumption burner and second is pre-mixed burner. To know more about these burners, please watch my previous video. The link is given in the description. Then comes monochromator. Either prism or diffraction gratings are used as monochromators. The transmitted beam from the flame enters the monochromator, which is allowed to fall only one wavelength at a time on photomultiplier tube. Then comes photomultiplier tube. The transmitted light from the monochromator, when falls on PMT or photomultiplier tube, the current is produced. This current is proportional to the light incident on the photocathode of the PMT. And finally, there is readout meter. This dial will give us the amount of radiations absorbed by unexcited atoms present in the ground state in terms of absorbance. So let's discuss the working of this instrument. The cathode and anode is connected with the power supply, from where we supply the potential of 500 to 1000 volt. The gas taken in the bulb is ionized. The cations of the gas are moving fast towards the cathode and remove atom from the cathode. These atoms strike with the gas ions and transition takes place. When they return to original state, they emit the characteristic radiations, which passes out of the quartz window and are incident on the rotating chopper. It produces intermittent radiations, which are incident on the unexcited atoms present in the flame of the burner. These atoms absorb the radiations. The transmitted light is incident on the prism, which is connected to the PMT. In PMT or photomultiplier tube, current is produced. PMT is connected with readout meter, which gives the absorbance. Now, by applying the Beer-Lambert's law, we can find out the concentration of unknown solution by knowing the absorbance. So what are the applications? First, quantitative analysis can be done using calibration curve method. Second, very low concentration, which is around 1 ppm or less, can also be analyzed accurately with the help of AAS. With the help of atomic absorption spectrometer, we can detect the toxic elements such as copper, nickel, zinc present in the food products. The phenomena is used to estimate sodium and potassium present in the blood serum. How much amount of lead is present in the petrol can be found out with the help of atomic absorption spectrometer. Soil extracts, plant materials, fertilizers, etc. have been analyzed for determination of sodium, potassium, copper, manganese, molybdenum, vanadium, etc. The amount of titanium and vanadium present in the steel alloy can also be determined with the help of atomic absorption spectrometer. But then also this method is having some limitations, like simultaneous analysis of many elements is not possible. Metals like lanthanum, tungsten, silicon, etc. form the stable metallic oxide and so cannot be analyzed. For alkali metals like lithium, sodium, potassium, etc., which have low ionization potential, in such cases, low temperature of the flame is required to minimize the ionization of the elements. Each element requires a separate lamp. If the sample contains two elements which absorb the light of same wavelength lambda, for example, manganese and gallium, both absorb at 403 nanometer, cannot be analyzed. In such case, we must remove the interfering radical. If you like this video, please click on the like button and also subscribe to my channel and press the bell icon to receive the latest updates.